came out of being human.
Possibly. But anyway, hello everybody. We're a pretty full house today. Nice to see everyone. How's it going? You guys ready for the fall? Ready for fall break?
For sure, yeah.
Ready to get this over with? Is anyone? Is anyone? Is this the last class for anybody? Or does everyone have Friday classes? All Friday classes. That sucks. Sucks to be you guys. This is my last class of the week, for example. But anyway, then let's get through it. Let's get through it and get you guys to Friday. We'll almost be done. So let me share my screen here and get started. Welcome back. We are still talking about section 6.1, which is, wait a minute, I'm going to do this, and then I'll even do this. There we go. We're talking about section 6.1. And I'm going to write /6.2, which is sets. And I say /6.2 because I just kind of found out today, I was rereading the book and I was seeing, because, you know, I like to stick relatively to the order of the book and kind of what we do, but I don't do it exactly. And I find out that I hate the way the book does chapter 6, because what they do is, like, you know, everything we've been doing with sets and subsets, where we talk about, like, oh, how do you prove something's a subset of another set, and how do you prove two sets are equal, and things like that along those lines. They don't do that all in one. They introduce subsets, and then they do a bunch of stuff, and then, like, a couple chapters later, they actually prove it. Or actually, the next chapter, they actually show how you prove a set to subset of something else. Why not just do it while you're talking about it, right? I'm no one, I guess, to complain about someone jumping around topics. I guess that's men in glass houses can't throw stones. But anyway, the point is we are here now, so we're basically doing 6.1 and 6.2 at the same time simultaneously because I say so. So today, though, let's get going and talking about what we left off with last time, and that is set equality. There we go, set equality. So we say, this is what we talked about last time, A equals B. So two sets are equal if and only if they contain exactly the same elements. So that's what it means for two sets to be equal. And by the way, you guys should know that equal signs are not to be used everywhere. They mean specific things and they're always defined. So for example, the equal sign with numbers is defined. Saying two numbers are equal means that the same number means something. Saying two sets are equal means they contain the exact same elements. But not everything has equal signs between them. We also use equal signs with matrices because we've defined it with that. If you go back in the literature of math enough, there's a definition of what it means for two matrices to be equal. But we don't use it for everything. For example, for sets, well, that's a different thing. The point is just be a little wary of that. But we do say sets are equal, use the equal sign. They're equal if and only if they contain exactly the same elements, which I think makes sense. That's kind of fits our conception of what it would mean for two sets to be exactly the same. And the way you could write this formally, I'll say, i.e., what this means is that A equals B if and only if A is contained in B and B is contained in A. So this is the formal, more mathematical way to look at this. And on the surface, they might seem kind of different. Like, this is saying that they contain exactly the same elements. This is saying they contain each other. Why are they the same? Well, let's start here, right? How would you ever, what's it mean for two sets to contain exactly the same elements? Like, what does this mean? Well, what that means is they contain exactly the same elements. So for one, for all x in A, since they contain the exact same elements, X must be in B. Right? We must have that be true. But also, we want to make sure that every X in A is in B. We also want to make sure we don't miss anything. We want to make sure there's not anything in B that's not in A. So a way you could write that is there does not exist an element in B such that X is not in A. So this says everything in A is in B and nothing in B is not in A. So we want to and here, I guess. But heck, what is for all X in A, X in B? Like, how can we write this? If every X in A is also in B, what do we know about A and B? I know you guys know this. You guys got this. If every X that's in A is contained in B,
For all X in B, then X is in A.
well, not necessarily, right, Safa? But thank you for thinking, though. Like, for example, if we had like 1, 2, 3, and 1, 2, 3, 4, right? Everything in this set's in this set, but not everything in this set's in this set, right? 4 is in this set, but not here. But if you can prove that everything in A is in B, so every element in the set A is contained in B, that means the entire set A is contained in B. This is the exact definition for A is a subset of B. Right? This is what we learned like 2 classes ago. This is the definition for A is a subset of B. And then let's deal with this, right? If we don't have, so if we know that there doesn't exist an element of B that's not in A, well, what this is really saying is that for all X in B, X is in A. If you distribute that negative correctly and you negation correctly and you flip the quantifier and do what you're supposed to do, you get that. But what is this?
Is that B is contained in A?
Exactly. This is saying that everything in B is contained in A. So all of B is contained in A. This is B is contained in A. So the point is, that's why these two ideas are the same. If A and B contain exactly the same elements, that means everything in A has got to be in B and everything in B has got to be in A. That's what it means to be the same. And one really easy way we can look at this is through the lens of Venn diagrams. And so this is the Venn diagram way to look at it. And I'll say Venn diagram. If A equals B, right, that means like if this is the set A, well, the set B is just exactly this, right? A and B are just the same thing. And clearly from here, you can see, oh, well, if they're equal, then A is inside B because A just is B, and B is inside A because B just is A, right? And this works the other way around, right? If A is contained in B and B is contained in A, well, the only option is for them to be the same circle. Because if they weren't the same circle, then there would be something in A or something in B that wasn't in the other one, which can't happen because we're assuming A is in B and B is in A. But if they're the same circle, A equals B. So this is like 4 different ways to look at it. Anyway, this is what it means for 2 sets to be equal. Any questions? My finger looks really big, doesn't it? Like, look how big my left hand is compared to my right hand. I'm deformed. So anyway, so there we go. No questions? Then we can move on and do an example with this.